Our next circuit is the summing amplifier or adder and is shown here as a schematic. This circuit has two inputs connected at node A, and we'll call this node the summing point. Now, since the non-inverting input VP is grounded, we have the condition that VP is equal to 0, and because of the infinite gain for an ideal op-amp, we have that also equal to Vn. Now, this configuration is similar to the inverting amplifier on an earlier video, so we start by applying the KCL to write the sum of the currents entering the node A, which is the summing point. So basically we have the current I1, which is basically the voltage across R1 divided by R1. So that's the current. So V1 minus Vn divided by R1. We have the same thing associated with the voltage source V2, and we need to find the voltage across R2. So in this case, it's just the voltage across R2 is V2 minus Vn. Note Vn is where the summing point A is located. And we take that voltage difference of R2 and we divide it by R2 using Ohm's law. Then we have also coming into node A is the feedback current. And that's simply because I labeled the direction going inside of node A, it will be VO minus Vn divided by RF. And the outgoing current is minus IN, and that's equal to 0. But we note for an ideal op-amp, IN is equal to IP, which is equal to 0, since the ideal op-amp has infinite resistance. So using these two characteristics or constraints associated with an op-amp, we can simplify this equation that I just written down such that I can cancel the Vn's and the IN's. Okay, with this simplification, let's solve for VO, where VO is given as the ratio of RF divided by R1, there's a minus sign here, times V1, and minus RF over R2 times V2. Now, to put it in block diagram form, we'll define this ratio of negative RF R1 as K1. So that's negative R1 over over R1, and K2 is equal to negative RF over R2, and now we can say that VO is a combination of V1 plus K2 V2. So here we have V1 times K1, where K1 is defined as minus RF divided by R1, is summed with V2 times K2, where K2 is minus RF divided by R2. So this is our block diagram form of the schematic, and we can generalize our result VO to be a combination of n inputs, and we can easily extend this concept to more than two inputs to n inputs, where we define VO is equal to K1 times V1 plus K2 times V2 all the way up to Kn times Vn by adding more inputs. And basically we have just more KCL equation expressions here for each of our voltage sources. Now let's look at the special case where we set R1 equal to R2, which is equal to R, and with this special case then VO is equal to factor out minus RF over R, and now we have V1 plus V2, hence that's why the output is a sum of basically proportional to the sum of the two inputs. and hence the name summing amplifier, or more precisely inverting summer. So that concludes the analysis, the op-amp circuit analysis associated with this summing amplifier.